Today we're going to be going through chapters 21.2 and 21.3 of our textbook, which covers sources of electric potential, a little bit about conservation of energy, and some calculations on electric potential. So one of the big things today is going to be this equation, the mathematical relationship between electric potential energy, which is the U, and electric potential, which is the V. So I'm going to write that out. U is electric potential energy, and V is straight up electric potential. So we talked briefly about the difference between these two things in the last video. And the deal is that V, electric potential, is a property of space. So a charge somewhere will generate a field, and a property of that field is the potential. Now, when a charge enters that field and enters the area with potential, it gets a certain potential energy, which is this U. So this is a property of an object or a charge. And the charge of that object in the equation is over here as Q. So, entering an area that has electric potential gives a charged particle an electric potential energy. And electric potential, which is the V here, it has the unit of joules per coulomb, which is also known as a volt, and we'll see how that relates to voltage here in a second. So a brief side note that's kind of a little bit of a picky point, but one that needs to be covered nonetheless, is that a choice of zero potential is arbitrary, just like anytime you work in gravity. So when you worked with gravity, you usually set the ground as the position with potential energy equals 0, and you would gain potential energy as you go up. However, you could have set that potential energy equals 0 to be wherever you liked, because most of the time, or pretty much all the time, you're just dealing with how much that potential energy changes. And that will be the main thing that we deal with in electric potential energy, is seeing the difference in potential energy and the difference in potential as a field. So the equation for that is here. It's pretty obvious. Delta V, delta means change in, equals the potential at point B minus the potential at point A. And potential differences are created by separating charges. An example of this that we'll take a quick look at is a capacitor. So, a capacitor is two charged plates that are equally and oppositely charged. Now, if these two plates are together, right next to each other, well, the big deal is that they're both conductors, so the charges will equalize, and there will be no difference in potential because there will be no field that is created. But as soon as you separate those two plates, you get a positive side and you get a negative side. There is a difference in potential. This separation creates a field, and that field creates a potential difference. A kind of odd consequence of this is that when any conductors are connected, they're going to have a potential difference of 0 because the charge spreads out evenly over the whole thing, so there's no separation of charges. And that is, of course, assuming no internal resistance, because as we'll see when we get to circuits, things that do have resistance do have a separation in charge, and we'll look at it when we get to it. Right now, we're just going to assume there is no internal resistance. So we do have to talk real quick about the behavior of charges in potential differences before we talk more about the potential difference themselves, because it's different for positive charges and negative charges. Positive charges are pretty normal. They move from high to low potential, as one would expect. However, negative charges move from low to high potential. So if you think about, potential as like kind of a topographical thing where places of high potential are more like hills and places of low potential are more like valleys, and that charge is going to flow from high to low places. Positive charges do that. However, negative charges, weirdos that they are, decide to go uphill and go backwards. And this is just because negative charges behave oppositely of positive charges by nature. They experience the same fields in the opposite direction. They experience the same forces in the opposite direction. So it makes sense that when they behave in a potential difference, they go in the opposite direction. So when we're working with potential, since it's a scalar kind of a thing instead of a vector kind of a thing, we do use the sign of the charge in calculations to make it a little bit easier. This pretty much takes care of figuring out what positive versus negative charges are going to do, but you do have to be mindful that you can use it here in potential difference, but you cannot use it mathematically in forces and fields. You have to do it qualitatively. One thing that we're all super familiar with that does create a potential difference is a battery. Batteries use chemical processes to create a potential difference, which is going to drive a circuit. So to think about how that works, it's basically like this. This is the battery in a circuit. Circuit's here. We do need a resistor in there if you're familiar with circuits. And the electrons are going to start off, because electrons are electricity flowing, they're going to start off on this side, and they're going to make their way around the circuit. And basically, what this means is that the electrons are falling as they go. So this is like downhill for them. Okay? They're going downhill. And, well, they're going downhill for electrons, which is uphill for protons. They're going downhill. And when they get to this battery creates a potential difference. One side is the bottom of the hill. The other side is the top of the hill. So between here in the battery, what the battery does is it takes them from that low energy and pushes them up to the top of the hill so they get enough energy again to go back around the circuit. And it'll go forever until the battery gets worn out. So batteries create that potential difference, which gives the electrons enough energy to keep flowing around and drive a circuit. So our next little bit is about electric potential and the conservation of energy. And we're going to look at using gravity as an analogy once again, because really it's a pretty great analogy. And to do that, we're going to look at roller coasters. Roller coasters are like the quintessential example of conservation of energy. And that's because it's really easy to see that when a car or a train on the roller coaster goes from a place of high potential, so we got high potential energy up here at the top, to low potential, where that would have low potential energy, that it gains speed. So what it loses in potential energy, it gains in kinetic energy. And then as it goes up a hill, say over here on the loop-de-loop, as it goes up, it's going to lose speed. It's going to get slower. But as it loses that speed or kinetic energy, its potential energy becomes higher. So really, all that's ever happening is that the cart is going from high potential energy and low kinetic to low kinetic and high potential. It's just transferring energy back and forth between kinetic and potential. And we're going to see that that's exactly what charges do as well. So here's all of the equations involved in that, and I'm going to walk you through them. So just like in gravity, we had a total energy of the train. It had an energy that was its potential energy, mgh, plus the kinetic energy, 1/2 mv squared. And as that transferred, the total still had to be the same. So this would be like mgh 1 and 1/2 mv1 squared is going to, as a total, equal the same mass times gravity at a later height plus 1/2 mv squared of a later speed. So over the course of the roller coaster, the total energy never changes. It just changes on which type has more, kinetic or potential. That same thing happens with charged particles. So this K is kinetic energy, which is calculated the exact same way, 1/2 mv squared. And this U is the potential energy of the charge, and it's electric potential energy. So if you remember from earlier, the equation for electric potential energy is QV, and here we've got QV final and QV initial. So really, all of this equation is saying is that your kinetic plus your potential at one position has to equal kinetic plus potential at another position, because that's just conservation of energy. Whatever energy you start with, you have to end with. Now, if we rearrange this equation a little bit, we'll arrive at this one on the bottom. So if you do, let's see, I'll write it over here on the side. If you do KF minus KI, so you move the KI over, and you move the QVF over, you get KF minus KI equals QVF, negative QVF plus QVI. So what that can be consolidated as is the change in kinetic energy, F minus I, equals negative Q VF minus VI, which is change in V. So your change in kinetic energy is negative the change in potential, which is consistent with what we should know about conservation of energy from AP Physics 1. So if we want to calculate a change in potential based on the initial speeds and final speeds of a particle, or if we want to calculate the potential difference based on the way a particle's speed changes, we can use this equation. And as a real quick application and a side note, we're going to talk about the electron volt, which is a unit of energy. So an electron volt is defined as the kinetic energy gained by an electron if it accelerates through a potential difference of 1 volt. And we're going to plug that into our equation that we just saw and see how to convert between a joule and an electron volt. So change in K is the kinetic energy gained that we're looking for. So we're going to look for the change in K by an electron if it accelerates through a potential difference of 1 volt. So that change in K is going to be equal to negative Q. So that's negative, and the charge of an electron is negative. Remember, we can use it when working with potential difference. So negative times negative 1.602 times 10 to the negative 19 coulombs times a potential difference of 1 volt, which is 1 volt. 1 volt is joules per coulomb. So what you can see is that the change in kinetic energy gained by the electron, which is 1 electron volt, equals negative 1.602 times 10 to the negative 19 joules. And this is a standard unit of energy to use when working with small electric particles. However, anytime you are working with something else, something in mechanics, or with any other constant that involves regular SI units, you have to make sure to convert that to joules. Now, I know that doesn't seem like a whole lot, but we're going to do a few questions just to check and be sure that you guys know what you're doing. So this one says, positive charge moves as shown. Its kinetic energy does what? So we look at this positive particle as it moves through a capacitor. And let's just think about it. A positive charge gets what? It gets repelled by other positive charges. So as it moves closer to these positive charges, there's going to be a force on it going that direction. So if the force is going that direction, it's going to be slowing down and decreasing. And that's because this plate is going to be doing work on it in that direction. Its force goes that direction, and its distance goes this direction, so the work is going to be negative. And when the work is negative, the kinetic energy is decreasing. That's the work energy theorem. And we can see that's correct. All right, next question. A proton is released from rest at the dot. Afterward, the proton does what? So right here, we've got a proton. Proton is positively charged. And we know that a positively charged particle moves from places of high potential to places of low potential. So at its 0 volts, it's going to move towards the place of low potential, which is downwards towards the negative 50 volts. And as potential energy decreases, according to conservation of energy, kinetic energy must increase. So it's going to move downwards and it's going to speed up. So that answer choice is E, moves downward with an increasing speed. And yep, that is correct. Next up, if a positive charge is released from rest, it moves in the direction of A, stronger electric field, B, a weaker electric field, C, higher electric potential, D, lower electric potential, or E, both B and D. And the answer here is D, lower electric potential. And the answer here, why it's not also B, is a little bit nitpicky. But the direction that a charge is going to move in an electric field is not towards a weaker area necessarily. It is to wherever the vector is pointing. So for example, if this is your electric field, let's say it's created by negative charge. And it looks like this. So we have a point charge that is right here, okay? It's going to move towards the negatively charged particle, which is because the field is defined as the force at that point. So it just moves in the direction the field is pointing, not specifically to somewhere where it's weaker. Because if it was going to move to where the field was weaker, it would move out here or to the side. But it actually moves in the direction of the vector itself. However, it's going to move towards a lower electric potential because that's simply how charge flows. And there we see the answer. All right, for the last little bit, we are going to look at a couple of examples that are non-conceptual, well, slightly conceptual, but have actual calculations. First one reads, a 15 nanocoulomb charged particle moves from point A, where the electric potential is 300 volts. So I'm going to go ahead and draw that. This is point A, where potential equals 300 volts, to point B, where the electric potential is negative 200 volts. Potential equals negative 200 volts. By how much does the electric potential change? All right, well, that one's not too bad. Change in potential is the potential at B minus the potential at A, which is negative 200 volts minus 300 volts. So it changes negative 500 volts. Cool. Next question, by how much does the particle's electric potential energy change? So this is based on the equation change in U equals Q times change in V. So let's plug and play. Delta U equals Q. Our Q is 15 nanocoulombs. 15 times 10 to the negative 9th coulombs times the potential difference, which is negative 500 volts. So the particle's electric potential energy changes this amount, whatever that is. I'm not going to actually type it in the calculator. So the potential difference didn't depend on the charge, but the potential energy difference does depend on the charge. Next question says, how would your answers differ if the particle's charge were negative 15 nanocoulombs? So let's first look at if the electric potential would change. So electric potential was this one. Change in V equals VB minus VA. And that was not dependent on charge at all. So the electric potential does not change because it's simply a property of the space, not dependent upon the charge. But the electric potential energy would change because instead of 15 nanocoulombs, we're now going to have a negative 15. So we'd have to insert a little negative in there. And our change in potential energy would be positive rather than negative. All right, next up. A proton moves through an electric potential created by a number of source charges. Its speed is 2.5 times 10 to the 5th meters per second at a point where the potential is 1500 volts. What will be the proton's speed at a short time later when it reaches a point where the potential is negative 500 volts? So this one is going to be based on conservation of energy. So let's look at the kinetic plus the potential for each side. So I'm just going to put K plus U. This is going to be initial, and this side is going to be final. So our initial kinetic energy is based off of this speed. And we know kinetic energy is 1/2 mv squared. So we need the mass of a proton. I'm not going to go Google it right now. So we're going to put mass of proton times the velocity squared. 2.5 times 10 to the 5th meters per second squared plus the potential energy of the particle. And that is Q times V. So that's the charge of a proton, 1.602 times 10 to the negative 19th times V, 1500. And that is the initial total energy of the particle. So it's going to reach somewhere where the potential is negative 500 V. And we're going to look for the speed, which we can find from the kinetic energy. So its potential energy after it has moved is still Q times V. Q is 1.602 times 10 to the negative 19th times the new potential, negative 500 volts, plus 1/2 mass of a proton, V squared. And it's very simple to algebraically solve from there for V. So really, all you're doing is potential energy and using conservation of energy to find it in conjunction with kinetic energy. All right, so now you've got a little bit of homework to do. This week I'm giving a weekly homework rather than a daily homework every day because that's a bit excessive. So go complete the parts that you can over, let's see, 21.1, 21.2, and 21.3.